In the previous video, I have explained you how the resistance of two resistors connected in series can be related to the length of pipes that we were using in our analogy. So let us continue from there towards our very interesting arrangement of resistors. Let me take a battery here, and connected to the battery I have this weird kind of an arrangement of resistors. I hope you can see that. Perfect. Now let us take this kind of an arrangement. At first this kind of an arrangement might look scary. I forgot the resistors. Yeah. There you go. This arrangement. So yeah, so we just have two resistors in series on both sides and then both of them in parallel. And if I have to represent this kind of a circuit with our analogy, I'll simply go step by step. Have the battery analogous to the large pump here, yeah, and then I have the parallel pipes. I'll draw them small here. Yeah, so these are like the low resistance wires. Now I have a division. I have two sections in parallel here. So what I can do is, to represent them, I can simply draw. So the pipe divides into two further smaller pipes. Let me take the first pipe here and the second pipe here. So I have this sort of an arrangement, and this is the first section of the pipe. So this section of the pipe is like this resistor, this section of the pipe is like this resistor, and then I have in front of this resistor I have another resistor connected in series. So after this pipe I have, just to show you another section of the pipe, I have this section of pipe. So this section of pipe is like this resistor, and this section of pipe is like this resistor. Yeah, they're connected. And I can just complete the drawing by just completing this section. Wait, yeah, there you go. Yeah, so this is the analogous diagram that I have, that is analogous to this circuit here. And so I have four sections of pipe: first section, second section, third section, fourth section, and those four sections are similar to the four resistors I have here. Two pipes in series, two resistors in series, and then these two sections are in parallel and these two sections are in parallel. Simple, right? Now the length of the individual pipe represents the resistances of each of the resistors. So if this resistor is a large resistor, I mean this has a large resistance, so I'll have to draw a longer section to represent this this resistor, right? And if this one is large, I have to draw this section large, and so on and so forth. Now this part is simple, but now the interesting part happens when I connect a resistor this way. How do I draw that here? Well, it connects the junction between the series resistors on both the sides, right? So this is similar to drawing a resistor, drawing a pipe here. Perfect, right? Now if I have to figure out, let's say, so this is the positive terminal, so current flows from here, it goes into this, the current divides and flows this way, and then it comes and it should flow this way, and this way. So that part is clear. But what happens, will the current flow from, so in this section here, will the current flow from here to here, or will the current flow from here to here? Now that is the part that we will be focusing upon, and I'll use this diagram here to explain that. How do you figure out which direction the current flows? Now assuming, let me just take some values here. Let's take 2 volts, 2 ampere, 2 ohms, sorry, and 4 ohms here, and let's take 5 ohms there and 10 ohms there. So now we know that in a given loop the potential drop has to be equal to the potential of the battery. So let's take a 3 volt battery. So we know that if we take this loop, this loop, right? So the potential drop occurs across these two resistors, and the potential drop should be 3 volts, which is similar to, so here in this case, if I take this loop, so the water can travel through the pump, through this pipe, and down this section and back to the pump. And so the potential drop in potential energy has to be equal to this much, this height, this difference in height times mg, right? So now how long should I draw the two sections of the pipe? Well, I can clearly see that this one is 5 ohms and this one is 10 ohms, and because the potential drop occurs across these two resistors, and I know from the last video on voltage divider that this thing should act as a voltage divider. This thing has double the resistance of this one, so the potential drop should occur in the similar ratio, right? So the ratio of resistance of these two resistors is 5:10, which can be simplified to simply 1:2. So the drop in potential should be in this ratio, right? And I can actually figure out because this is a 3 volt battery, the potential drop should be 1 volt across this one and 2 volts across this one, right? 1 plus 2 is 3. Yeah, that makes sense. Now if I have to draw that here, I can simply draw these two pipes in the ratio of their length. So the ratio of the length of these two pipes should be 1:2, and yeah, I hope I have drawn in that similar manner. So so this pipe is actually double the length of that pipe, and yeah, that seems this pipe seems double the length of that pipe, so I don't have to change that. Now if I look at this section of the circuit, if I look at this section, the resistances are in the ratio of 2:4, which can be again simplified to 1:2. So again the resistance is in the ratio of 1:2, and again I can figure out that the potential drop would be similar, 1 volts here and 2 volts here. 1 volt plus 2 volts is 3 volts, so that also makes sense. I'm talking about this loop, if somebody's confused. The current goes from here to here to here, through this and back here. So again the potential drop should be in the ratio of 1:2, because the resistances are in the ratio of 2:4 or 1:2, and so the potential drop should be 1 volt here and 2 volts there. And again I can draw these two pipes, the length of these two pipes should also be in the ratio of 1:2 to represent this section, and yeah, the length of this pipe is double the length of that pipe. Now if I focus here, if I join the junctions of the two pipes on both the sides using the third pipe, which represents this resistor, I can see that because the ratio of length of both the sections, this section and that section, is the same, 1:2, I can see that the pipe in the middle is actually parallel to the ground. Now that is a very important part. This pipe is parallel to the ground. So what do you think? Will water flow from this side to that side, or from this side to that side? Well, the simple answer is water will not flow through this pipe. Why? Because water always flows from a higher point to a lower point, but both these points are at the same level. So water should neither flow from here to there or there to here. I hope that makes sense, right? So obviously this pipe will get filled with water, but the water will stay there, it will not move, because the pipe is completely level and the water should not move, right? And so that also means that there will be no flow of current in this resistor. That is the weird and amazing part of this. There will be no flow of current when the ratio of the resistances on this side is equal to the ratio of resistances on this side. And here we can see that the ratio of resistances is 1:2, and even here it is 1:2, and in this case we end up getting no current in the central resistance. Just to make matters a bit more solid, I can tweak I can just change the ratio. So instead of having, so I'll keep the resistance on this side as 5 ohms and 10 ohms, but let me change the resistor on this side. So let this resistance be 2 ohms, and even this one let it be 2 ohms. Now the resistance on both the sides, so the resistance on this side is in the ratio of 5:10, and that is simplified as 1:2. So again the potential drop will be similar to before, 1 volts and 2 volts, because that is in the ratio of 1:2. But in this case here the resistance is in the ratio of 2:2, and that can be simplified as 1:1. And so the potential drop across this resistor and that resistor will be equal. So this 3 volts has to be dropped across these two resistors equally. So there'll be a 1.5 volt drop here and the remaining 1.5 volt drop here, right? 1.5 plus 1.5 is 3 volts. I'm just doing some small mental calculation there. And so what we can infer from there is, because these two have equal resistances, to represent them in this case I'll have to draw the two section of pipes of equal lengths, because both of them have equal resistances, right? So I'll just draw two pipes of equal length. I hope, yeah, there you go. And I'll draw the second section of, yeah, so I hope you can see these two pipes have almost equal lengths. And now if you see, in this case, if I now connect the two junctions using this pipe, you can see that the pipe is slanting downwards, and it is slanting, this section of the pipe is higher as compared to this section. So if now water comes from here into this section and comes down, now there'll be some water flowing in this direction through these two pipes, but also there'll be some water flowing in this direction because this side is higher as compared to this side. And if we have to apply the same logic there, there'll be some current flowing in this direction because this point is at a higher potential as compared to this point. How do I know that? Well, I have 3 volts here. If I go through this section here on this path, I can see that there's a potential drop of 1.5 volts. So the potential at this point is simply 3 minus 1.5, which is 1.5. So the potential of this point is 1.5 volts, whereas the potential of this would be 3 volts. On this side I have only 1 volt of potential drop, so the potential at this point would be 3 volts minus 1 volt, which is 2 volts. So the potential at this point is 2 volts, and I can see that this point is at a higher potential, 2 volts, as compared to this point, which is at only 1.5 volts. So there will be a current flowing in that direction, and if you have to find that amount of current, you can just simply find the potential difference, which is 2 volts minus 1.5 volts, 0.5 volts. And so the potential difference between these 2 points is 1.5 volts, and you can simply divide that voltage with the resistance of this resistor to find the current. But the basic idea behind all of this is, I'll just quickly end the video here, that when the ratio of these two resistances is equal to the ratio of these two resistances on this side, there will be no current flowing in this resistor. But if that ratio is not achieved, if the ratio is different on both the sides, there will be some current flowing, and you can figure out the current by using a bit of common sense, as I showed you just now. And such an arrangement is called a Wheatstone bridge. And how is it useful and why are we even studying it? That will be explained in the coming videos. But for now, I'll just tell you that this is called a Wheatstone bridge. This arrangement is called a Wheatstone bridge, and in case when the ratio of resistance on this side is equal to the ratio of resistances on this side, such a situation is called a balanced situation. So the Wheatstone bridge is called is in a balanced state, because the resistances on this side, the ratio of resistance on this side is balanced by the ratio of resistance on that side, so they are essentially equal, and no current flows through this resistor in such a case. And I hope you understand the logic behind why that happens. And yeah, that is it for this video.